So today, yeah, we're going to start 4.1. Like I was saying, this is the section that everybody kind of like takes a little bit for granted. I mean, about 75% of this you kind of can't because you're just it's gonna be infused in everything else we do. But sectors of circles and arc length are actually really important. So make sure that when you're studying and moving forward in the unit that you don't just kind of leave this behind, but everybody sort of, it's like, oh, I got it, and moves on and then doesn't revisit it. And you want to make sure that when we get to the word problems and stuff later that you're good at working with that. Okay, so the first thing that we need to talk about is, just to make sure that we're all kind of on the same page here, is we need to make sure that when we're working with this stuff, when you're spinning and rotating something, right, how you start and where you end up really matters, because you want to make sure that everybody's on the same page. And when we read the description in a problem, we want to make sure that you're drawing the right picture, because if your angle isn't in the correct quadrant, you will get a positive answer where somebody else will get a negative answer, even if you did all the intermediary calculations correctly. So we want to make sure we get the terminology and stuff down. So one thing to make sure that we understand, right, when we draw an angle, right, everybody's kind of used, right, to seeing this, right? So an angle, we talk about two lines, and it's going to be the rotational, right, distance between those two lines, right? But we have to make sure that we start and finish in the right place. So the initial side, oops, initial, spell right, there we go, is where the angle starts, okay? So that's where you draw the first line that you're gonna draw. Then you rotate toward the direction they tell you. So in this case, right, if that's the initial side, we rotate it up, right? And then where we stop, this line is called the terminal side. So this is really important in like word problems. If they tell you an angle starts in standard position and has a terminal side in quadrant blank, you need to know that's going to tell you where to start drawing your angle. It's going to tell you where to draw the terminal side, and then the angle is always between those two values. So you go from standard position to that. So terminal kind of means stop or end, so that's kind of makes sense, all right? Standard position, all right? So if we're doing a word problem and we have some kind of geometric shape, there'll be some reference in the problem on the diagram to what particular angle they want you to look at. But in just general terms, if we talk about an angle from standard position, we always assume that the initial side, okay, so this initial side right here is on the positive x-axis. So an angle, right, in standard position, it would look like this. So if I had the terminal side in quadrant 1, you start at the positive x-axis, and we default to going counterclockwise. That's how we go around. So any of you guys that kind of remember the unit circle from high school, right, we always started all the angles on the positive x-axis, and we rotated counterclockwise around the circle. And so that's just sort of the default setting. If we want you to do something different from that, there'll be some kind of indicator in the problem that you need to adjust from that. All right, so coterminal angles, right? Well, terminal means in, that's the terminal side. Co kind of think of means share, right? So what coterminal angles are is they're angles that have the same terminal side. So let's see what we mean by that, right? So let's just say that I have an angle in standard position, and its initial terminal side, right, is in the first quadrant. So I just have some angle theta, okay? If I want to find a coterminal angle, right, well, it means that it would also have to start on the same initial side and share the same terminal side, right? Well, if I just redraw what I just drew, well, that's just the angle I started with, okay? So the only way that you'll ever get back to this terminal side again is if I rotate all the way around my circle. So the first coterminal angle that's positive would look like this. If I bypassed it the first time, right, and came around the second time, and I'm going to call that guy alpha. So it's whatever theta is plus 360 more degrees. And I ended up stopping on that same terminal side. So I spun another 360 and I got right back there. And then I could go 360 again and I would end up on that spot, right? 360 again. So I could have infinitely many coterminal angles. Those would be positive coterminal angles. If I wanted to find a negative or a negative spin to give me a coterminal angle, well then I could start on the negative side, right, and go negative 360 around until I keep hitting that same spot. So that's all we mean by coterminal angles. So if we're talking about degrees, you want to add 360 or subtract 360 depending on what direction they ask you to spin in, right? And if we're working in radians, we would add or subtract 2 pi because that would be a full rotation around. But that just means keep going around again. So you can have angles larger than 360, right? So there are 2 units that we measure angles in. The first are in degrees. And we say that one rotation, right? That's the same thing as if they say one revolution, right? And in angular measurement, that's 360 degrees. So when somebody says in a problem how many rotations or how many revolutions, those are equivalent statements. And what we mean by that is complete 360 degree turns. If we measure in radians, well then one rotation or one revolution is 2 pi radians. Okay? So something to keep in mind about radians as far as units, especially if you ever deal with them in any other applied class, a radian is actually unitless. We write out RAD, or we'll tell you when you're doing something on a computer, we might put RAD in, but it's actually unitless. So when we get to word problems and we start doing some conversions, it'll seem like the radians just disappear sometimes, and that's because there's really nothing there. It's just a unitless quantity. We usually just write it for our own edification. But when you're dealing with a computer program, right, if you don't put the degree symbol in or somehow type DEG after the angle measurement, almost every calculator computer will always assume that it is a radian measure of an angle. If you don't specify degrees, it doesn't know that it's degrees. Now for calculators, we actually have degree or radian mode, okay? So you can have it in either or. But keep in mind that on a calculator, all degree and radian mode mean is if I'm using a trig function, like sine, cosine, it's just reading the number inside it. But if you're using a formula that's got theta in it, or an angle measurement, and it doesn't live inside of a trigonometric function, well, the calculator doesn't know that. It just reads it as any other constant. So you want to make sure that you're being really, really careful when you're working with numbers and knowing which one of these units you have to be in for some of these formulas. Typically, we do most things in radians. Now, when we start this unit, everybody's going to be like me. I was the same way. I got really hard-headed. I was like, radians are stupid. I don't know why I have to write pi all the time. 360 is such a nice number, and it's divisible by so many things. It's easy to work with, right? When we get a little bit deeper into the unit and we start to get toward the stuff at the end, you're actually going to see that radians make things easier, not harder. So in the beginning, it always seems silly and dumb. I don't know why I have to do this, right? But then when you get a little bit further down, you'll see that the radian stuff is actually a lot easier to work with. So one of the things that I find really interesting is what exactly is a radian, right? So kind of like when we had with E, and we knew E was an irrational number that had infinitely many decimals, and we were able to kind of figure out where that came from that compound interest formula. Radians, right, always involve pi. And pi is an irrational number. It's probably one of the most famous ones. All right, everybody like tries to memorize as many digits of pi as they can, okay? But what exactly is a radian, and why is pi 3.14, you know, all that irrational number version of it? So in order to figure out what a radian is, right, we need to talk about what an arc length and a sector of a circle is. So a sector of a circle is just like a slice, right? So it can kind of look like a slice of pie, right? It can be bigger, the angle in the sector could be bigger than 90 degrees, bigger. It can be any angle from 0 to 360, but it's just simply a piece of the circle. And a sector consists of 3 sides: the initial side of the angle, the terminal side of the angle, and then you also draw the actual piece of the circle itself, okay? So because this is a section of a circle, the terminal and initial side will always have length r, right? Where r is the radius of the circle. So that is the definition of a circle, right? Every point on the outside is r away from the middle. The arc right here, which is what we call this piece, right? We usually define with the letter S. And the length of that side is known as the arc length. And then, of course, right, theta is always going to be the angle measure that connects the initial and terminal sides. All right. So if we want to know what the arc length is, if we want to measure it, right, we can measure the arc length using the formula r theta. Right? Now, anytime, unless it is specified otherwise, but 99 times out of 100, if you were looking at a formula that has a theta in it or any kind of angular measure, that angular measure is almost always in radians. Okay, so if you want to calculate the arc length of this sector, and I told you that theta was 40 degrees, you have to convert into radians before you can plug it into the formula. And having your calculator in degree mode does you no good here, because the calculator would just read whatever number you type as a constant. If it doesn't live inside a trig function, it doesn't make the distinction between the two numbers. So theta, right, must be in radians. And so this is why I said people take this section for granted, because we'll give you a question about this like on the test, and one of the things we might do is give you the angle in degree measure, and that's part of what we're testing you on. Do you know you have to turn it to radians before you pop it in to the formula? We can also find the area of this sector, and there's actually multiple incarnations of this formula. So the first one that we can look at is 1/2 r squared theta, or once again, theta is in radians. But what if I don't know the angle measure? What if I just know r and s, okay? So by using the arc length formula, I can solve the arc length formula for theta and plug it in, and when I simplify, I'll get 1/2 r times s. So that's another way you could calculate the area. So if you plug in s over r, the r in the denominator cancels one of those r's in the numerator, and that's why you get rs, okay? But what if I've got a formula for r and theta, I've got a formula for r and s, but what if I don't know r, but I know theta and s, right? So if I want to get rid of s in the formula, oh wait, sorry, I got rs, or I want to have s theta, right? So I want to get rid of r. So if I want to get rid of r, I can simply solve this for r and get s over theta, right? Move the theta under. And when you plug that in, so if we say theta equals s over r, right? When I plug, oh, sorry, I did that wrong. R equals s over theta. When I plug it in here, I'm going to get 1/2 s squared over theta. So if you can just memorize one of these area formulas and you know the arc length formula, you can use algebra to solve for any variable. Did I do that right? I think I did, yeah. S squared over theta, yeah. You can actually solve for whichever two of the three you have. So there's actually 3 different ways you can calculate the area by just using a little bit of algebra manipulation. All right, so what is a radian? All right, so a radian, because radians were actually invented or discovered, or however you want to think about it, like many years ago, pre-technology. I mean, this is like an old thing, okay? So 1 radian, exactly 1 radian, okay, so this is how it was initially defined. So you have a sector of a circle, and the arc length of the sector is equal to the radius of the circle. So if I were to draw, right, this happens to be length r. These are already length r by default. That means this angle right here is exactly 1 radian. So what's really cool about this is all you need is something pliable like a piece of string. Okay, and I remember when I was in one of my classes, geometry classes in college, we had an extra credit question on a test where if we could draw exactly 1 radian, right, for extra credit. And so all we needed, if you were in class and paid attention to what the definition was, all you needed was a piece of string. So if you have the circle, you just stick one end of the string in the center, stretch it out to the edge of the circle, there's your radius, and then you would just bend it around the edge of the circle, right, till you, and then you would mark it, and then that was it. That was 1 radian. So you never needed a calculator, you never needed anything fancy, any fancy tools, but literally something as simple as a piece of string. You could find the exact 1 radian measure of any circle that you wanted. So this is actually kind of how radians turn into pi. So if you do the mathematical calculation to figure out exactly what a radian is, what you find out is it's like 59 degrees and some change, okay? So if you take 3 radians and put them together, stack them up, well, it's like very close to 180 degrees, but there's that little extra bit left over, right? So that's how they invented pi. Well, we need the straight line, right? So they just tacked on that little sliver that was left over, and that's why nobody really can figure out exactly where pi ends, because all that stuff after the 3 is just the angle measurement of that tiny little slice at the end. So if you actually go in and take 3 sectors of a circle that have arc length 1 radian and just stack them all together, you'll see they come very close to 180, but not quite. And so that's kind of how pi became that irrational, crazy number that it is. Okay. All right, so let's look at some examples and play around with all this stuff, and we can kind of see what we mean. So we're going to let alpha be 47 degrees, and we're going to find a positive and negative coterminal angle. So we can assume, right, unless it's stated otherwise, you get to assume that the angles are always in standard position. So if we're talking about standard position, right, we'd say the positive x-axis would represent like 0 degrees. We move counterclockwise around. So here's how, right, one rotation would kind of move around. So if you understand that every quadrant is 90 degrees, we should all be able to tell when you see an angle measure, as long as it's between 0 and 360, the quadrant should jump out at you. So we number the quadrants since we move counterclockwise around. We number the quadrants as this is the first, this is the second, this is the third, and this is the fourth. So we count around in the same order that we spin. So I kind of know right away, because this angle is between 0 and 90, well, it's in quadrant 1. So alpha, right, is right here. So a positive coterminal angle means travel in the positive direction until you hit the terminal site again. So positive spin is the standard spin, that's counterclockwise. So if I want to know what a positive coterminal angle is, well, I take 47 degrees and I add 360 because I'm spinning in a positive direction. And we get 407 degrees. If I then start at that terminal side and go in the negative direction until I hit it, right, that means we're traveling clockwise around, and so those are negative angles, so we subtract 360. So one of the things you'll notice on homework is some of the questions might ask you to find the next 2 or 3 positive coterminal angles. So if they wanted you to find 2 or 3 of these, well, the first one would be 360, right? Then you would add 360 to the result to get the next one, and then add 360 again. So you could just keep doing that as much as you wanted. Same thing here. If I said give me 2 negative coterminal angles, well, the first one would be negative 313. Then I would just subtract another 360, right? And we could do the same thing with radians, except we'd add or subtract 2 pi. Are we good? Okay. All right, so let's do the same thing with radians. So it's the same process, right? We would draw the angle, and in the positive direction, we'd add 360. So in radians, that's 2 pi, right? So if I want to find a positive coterminal angle, you take your radian measure and you add 2 pi. So you could just leave it like that, depending on the nature of the question, but if we wanted to consolidate that and get a common denominator, the common denominator is 7. So if I multiply the numerator and denominator over here by 7, I'm going to get 14 over 7, so this will simplify into 18 pi over 7. If we want to find a negative coterminal angle, we subtract 2 pi, and so my common denominator is still 7, so I'd have 4 pi minus 14 pi, right? So that's going to give me negative 10 pi over 7. All right, so any questions on that so far? Okay. So most of this stuff is the stuff you guys usually hold on to, but let's look at some word problems. So they told us this sector, right, of an angle has an angle measurement of 0.853 radians. So we're already in radians, we don't have to worry about that. And a radius of 15 centimeters. And we want to find the perimeter and the area. All right, so I'm just going to sketch a sector, right? So there's theta, there's R, and there's S. So to compute the area, we actually only need to ever have two of these three values. And there were three different versions of the area formula. And you choose the one that you use based on the information you have. So if I have theta and I have R, well then I want to use the area formula in terms of R and theta, which was R squared theta. I need to make sure theta's in radians. It already is. So calculating the area is just going to be 1/2 15 squared times 0.853. So that would be your exact answer. And so if I did a little approximation here, that's about 95.96 whatever, right, units were in squared. So if, oh, centimeters, they did give it in the problem. So whatever unit of length the radius is in, that'll be the squared units of the area, okay? Now, if we want to find the perimeter, and I don't know why, but this is something that always throws people for a loop, right? Doesn't matter what shape you're looking at, perimeter simply means add up all the sides, okay? So the perimeter of a sector is going to be 2R plus S. I don't memorize that formula, I just look at the shape and grab all the sides I see, right? There's two sides of shape R, one side of shape S. So notice though, I don't know what S is, okay? But I do know R and theta, and we know that you can find S by finding R and theta times each other, right? S is R theta. So rather than calculating S and then plugging it in, I can just say, well, let's replace S in our formula with R theta. So 2 times 15 plus 15 times 0.853. So I would probably have factored out that R just because I don't like the algebra. I don't want to type 15 twice, but it's okay if you leave it like this. All right, and so this works out to be about 42.80 centimeters. So perimeter is length, so you know it would be centimeters. Area is centimeters squared. All right, so everybody good? Okay, so now we're going to do something kind of fun. These are the problems I like because they're real world problems. All right, so we're going to assume that the Earth has a radius of 4,000 miles. So that's a good estimate. It's close-ish, but good enough for this nice round number, right? So we're going to treat the Earth like it's a perfect sphere, right? And the radius of the Earth is 4,000 miles. And this is absolutely true, but Athens, Georgia is at latitude 34 degrees north. And we want to know how far from the equator is Athens. So if you really think about it, right, the way we read direction on Earth is we're used to looking at maps, which are aerial views, and so when you look at a map, you're used to seeing north, south, east, west. You see your little legend, it kind of looks like, almost like the Cartesian plane, right? But what's crazy is when you start doing a problem in 3 dimensions on Earth and you start talking about north, south, east, west, people in their head want to make north, south, east, west, and that's actually not the way it works. It's actually this way, right? North, south, east, west, and then you have the sky and the ground, okay? So the Earth is a sphere, right? And no one lives inside of the sphere. We all live on the surface of the sphere. So when you're actually calculating direction from one location to another on planet Earth, you're really doing arc length. It's really an arc to get you there, right? And that's why airplanes, when you're flying cross country, sometimes they'll fly way north and then across and then back down again, because the further north you go, the distance around is smaller because you're talking about a smaller circle, right? So one of the things that we have to understand is we kind of all know what longitude and latitude is, right? Longitude are the lines that go straight, and in the US, that's usually what we use to distinguish between our time zones, right? And then latitude lines are the parallel lines to the equator. So what we've actually got here going on is if I draw, right, kind of a wonky sphere for the Earth, there's the North Pole. We'll let that be the positive Y direction. Here's the equator, right, and we'll let that be the positive X direction. So the equator, right, is sort of the belt. It goes around the middle, and that is 0 degrees, right, in latitude. Any latitude lines above that mark, right, we say they're north in the northern hemisphere. Any latitude lines below that we say are south. And if you notice, 0 degrees, right, is the equator. And then it goes up to 90 when you get to the North Pole, right? It goes down to 90 when you get to the South Pole. So rather than using positive and negative angles, we use north and south to mean above and beyond, right? So 34 degrees, right, is going to be something like this. So here's Athens, right? And what this means is if I use this as the equator as standard position, and I draw the terminal side from the center of the Earth to the location on that latitude line, that angle is 34 degrees. So even though they look like parallel, like horizontal lines on a map, what that's really telling you is if you drew the angle back to the center of the Earth, that it would have that angle of 34 degrees, all right? So the distance from the equator to Athens is actually, and I'm going to just draw it over here so we can see it a little bit better, but if that's Athens, right, and the equator's here, what they're really asking you to do is find the arc length. So this is the radius of the Earth. This would represent the radius of the Earth. And this angle inside is 34 degrees. So that's something to keep in mind. These are actually very, very simple problems if you understand that every distance between 2 points, in this case, are going to just be arc length, okay? So arc length is just r theta. Well, r was given in the problem as 4,000 miles. Theta was given as 34 degrees, but I have to convert degrees into radians. So just like if you were converting miles into feet, right, you just have to know the relationship between the two variables. So we know that pi is 180 degrees. So you can see here degrees would cancel and you end up in radians. So if I actually type this into my calculator, and you guys all should have a pi button on your calculator too, which is nice. Don't ever just use 3.14. We get that Athens is approximately 2,373.6 miles from the equator. So another little fun trivia fact, you know when you're driving and you see a road sign and it says you're X number of miles from this city or everything, I always used to wonder when I was a kid, well, what point are they talking to? Because once you learn distance, right, distance is to a specific spot. And so typically it's City Hall. And so whenever you see the road sign, that is the distance to City Hall of that, you know, and that's kind of one of the things. So it's usually the City Hall or the courthouse, depending on how old the town is, that might have been, and usually those were in one place. So, all right, so let's look at another one. So this is a kind of a continuation, right? So we're still going to assume the radius of the Earth is 4,000 miles, but St. Louis St. Louis and New Orleans are at the same longitude, right? However, St. Louis is at latitude 38.62 degrees north, and I'm going to abbreviate New Orleans is NO, right? New Orleans is at 29.97 degrees north. And we want to know how far apart are they from each other. So believe it or not, this is how people used to navigate on the ocean, on the water. You had maps and you knew the latitude and longitudes, and you would literally, that's why they had sextants and they look like protractors, and they were measuring angles, and they could do a quick calculation and actually figure out how far they were nautically from it doing this. So here's what this means, right? So if they're at the same longitude, it means they're sitting technically right above each other, right on the Earth, but they have different angle measures back to the equator. So it's going to look something like this. So if you measure the arc length down, right, St. Louis is higher, so it's going to be right here, right? And New Orleans is going to be like somewhere here, and then the equator is the initial side. So what we're saying, right, is the angle to here is 29.97, and the angle all the way to here is 38.62. Right, so the arc length in this case is the longitude line, right, and they're on the same longitude, but you got to go further north, right, to get to St. Louis from New Orleans. So does anybody have an idea of what we probably have to do to find the distance between them? So what I want to do is I want to figure out what that is.
So we're finding S.
We are finding S, but I don't want S of the whole thing. I only want this little piece, right? So those angles are both measured back to the equator. So if I calculate S for each location, it's going to give me the distance as they are from the equator, like we did for the Athens problem. So if I take St. Louis's distance back to the equator and I subtract New Orleans' distance back to the equator, I'll end up with just that little piece at the top. Does everybody see that? Okay. So what we want to do here is we want to do, right, St. Louis minus New Orleans. So St. Louis's distance to the equator is going to be R, which was 4,000 miles, times its angle measure, which was 38.62, and we have to convert that into radians. New Orleans is going to be 4,000 miles times its angle measure, and we need to convert that into radians. So this is about 2696.2 miles. And this is 2092.3 miles. So that means if I subtract these two guys, I'll get how far apart they are. And so it's about 603.9 miles. So, you know, we all take our GPS for granted, but this is like the old school way of how you would calculate if you knew. And that's why if you know the latitude and longitude coordinates of a location, And so a really fun thing to do is if you've never played with Google Earth, if you get on Google Earth and you can spin the ruler around and zoom into places, if you click anywhere, it'll actually give you the latitude and longitudinal coordinates of like wherever that exact spot is. But if you know that, you can figure out where you are. Mm-hmm.
Could you just subtract the two angles to find the angle between SL, the St. Louis and New Orleans? And
You
then
can also do that. Yep. That would be, yep. Did everybody see that? So you could just find the angle difference and then only calculate S for that arc length. Yep. Mm-hmm. But you still got to make sure you convert it to radians. Yep. Mm-hmm. Cool. All right. Let's look at one more before I'll get back your test. Okay, so we have a ceiling fan and we want to determine its angular and its linear speed. So RPMs is revolutions per minute. That's actually is a speed, okay? So really this question is just playing with units and just converting to the correct units. So 90 RPMs is 90 revolutions per minute. So that's what that looks like, right? Angular speed, we typically write that in radians per some unit of time. So radians per second, radians per minute. So because they didn't specify, we can just keep everything in minutes to just make our life easier. So if you want to be in radians, right, we know that one revolution is 2 pi radians. So if I multiply this out, I'll get 180 pi, right, radians per minute. So we sometimes use the Greek letter omega, lowercase omega, for angular speed. So that's the angular speed. But if I want to find the linear speed, right, and so what we mean by linear speed, when something's rotating, right, especially like a ceiling fan, well, it's just spinning in a circle, right? But what if one of the blades were to fly off the fan, right? Or I taped a penny to the blade and then it flew off the fan. So when something's spinning in a circle and a projectile leaves it, it's going to leave it in a straight line path because the thing is whichever direction the fan blade is at the moment, it's going to fly off in a straight direction. So when we talk about linear speed of a rotating object, we're basically saying, well, with what speed would something fly off in a straight line if it bounced off? So the way that we do that is we say, well, linear speed is simply the radius times the angular speed. And it's not a coincidence that the arc length formula, which was distance, was linear distance equaled the radius times angular distance. S was r theta, so V is r omega. And if you go take a physics class and you actually get into acceleration, you find out that acceleration is r times alpha, which is angular acceleration. So all you do is take the angular quantity, multiply times the radius, and it gives you the linear quantity. So this is straight derivative of the arc length. So if we take the omega we just found and then multiply it by the 2 feet of the fan blade, oops, sorry, this was radians per minute, right? Well, 2 times 180 is 360. And remember, I told you that this is where it comes in that radians are unitless, right? We're multiplying radians by feet, but actually just feet come out because there's actually radians aren't actually a unit. And we get 360 pi feet per minute. So that would be the speed that something would fly off this particular fan if we rotated it around.